Okay. So Newton's method, basically what you're doing is you're approximating a zero of a function. It is an iterative method, meaning you have to do it over and over again. And as you do it, you use the derivative to approach the zero. So every time, each iteration, you get closer and closer to the zero. So this is the formula right here that we're going to write down in a minute. So you have like an initial guess minus the function at that initial guess divided by the derivative at the initial guess. And then once you get that answer, that becomes your x2, right? You plug that guy over here and you do it again. And then again and again. As you do it, each time you do it, it gets closer and closer to the actual zero. So the theory is interesting, but the mechanics is just basically this formula. This is why we do this in programming. It's not fun to do this by hand. The guy who discovered this, Isaac Newton, was doing this by hand way back when, right? So it was not very useful before we had computers. But anyway, so that's what we're going to do. The homework is going to give us basically an initial guess and a function. So we have to find the derivative ourselves. And that's going to go right here. And then you plug in, oh, well, the derivative is right here, but at x equals 1. And then the function at x equals 1. You do it one time, you get an output. That output is going to be right here. So when you plug in the 1 and everything's said and done, you get this. Then you plug that into that into where the xn is at. And you do it again, you get another one. And you plug that in, you get this guy. And you keep going. That's the idea. So let's go ahead and do the homework. Three 3.8. Okay. So the first one, they have you do it piece by piece, which is kind of annoying, but it's just because you're first time doing it, they want you to take it easy. So you plug in the 2 into here, and that's the output goes here. Then you find the derivative, right? Which is in this case 2x. So plug in 2 in here and you get the 4. 2 times 2 is 4. And then you divide 4 by this guy and you get this result. All right, 1 over 4 is this. So let's do that by hand, but I'm going to do the whole thing at once, not piece by piece. Let me write down the the formula too. So I think this is the easiest section in chapter 3. .8 Newton's method. F of x is equal to x squared minus 5, where x1 is equal to 2. So this is what's given. They are asking us to do 2 iterations of Newton. Dang it. All right, so we're going to have to find the derivative first. Right. Now, the formula is that xn is equal to xn plus 1 minus the function. I'm sorry, that's backwards. I should say n plus 1 is equal to this xn minus f of xn over f of derivative of xn. So this is our formula. So in other words, to find x2, we got to take x1 minus the function at x1 over the derivative at x1. Okay, where x1 is 2 in our case. So that'll be 1 minus f of, no, I'm sorry, this is 2. This would be 2 minus f of 2 over the derivative at 2. So this would be 2 minus the function at 2, which is 2 squared minus 5 over the derivative at 2. So this will be 2 minus 4 minus 5 over 4. 2 minus negative 1 over 4. 2 minus minus 4, that's just going to be 2 plus a fourth, which is, what is that? 9/4, right? So this right here is x2. Does that make sense, what we're doing? We're just following this formula here. We found x2 by plugging in x1 into the function divided by x1 in the derivative. We eventually get 9/4. So now to do the next iteration, right, because it says they wants us to do 2. So I'm going to do it over here. x3 is equal to x2 minus f of x2 over the derivative at x2. So that would be 9/4 minus f of 9/4 over f prime at 9/4. Okay. So that will be 9/4 minus, it'd be an ugly fraction, right? 9/4 squared minus 5 over 2 times 9/4. I'm not going to do that by hand because that's just stupid. It looks ugly. I should be 2. Once you use your calculator, that'll be 2.2361. Okay. I'm going to separate this. Does that make sense? Do you see how all we're doing is using a formula? Are there any questions on how to do Newton's method? So we were given x1 and a function. We use this formula to find x2. And then we did it again to find x3. Now, just for fun, let's say we wanted to graph it, right? And look at the zero ourselves. Honestly, this might be this most likely is one of the methods your calculator uses to figure out what the zeros are. Let's check it out. This is what we had right now, right? 2.236, right? So we were pretty close just doing it twice. So the more iterations you do, so if you were to code this on your computer, you could tell it to do like 100 iterations or 1,000, and then you'll get even more accuracy. But after a certain point, there isn't much change. It's most likely not going to change. It might change over here in the 7th or 8th decimal place, but not here. Any questions on the idea of Newton's method? Do you see what it does? Do you see how to do it? So that's all you're going to do the entire time. Let's do another one that's different. Oh, this, I'm not going to do this one, but well, I guess we could. Apply Newton's method to approximate the x values of the indicated points of intersection. So what they want us to do is find these intersections. Right. So remember, Newton's method finds zeros, right? So if you create a new function of f minus g and set this to 0, you will find these sections. So we're going to create a new function. We're going to use h in order to find the two intersections. Okay. And they want us to keep going until it has less than 0.001. So that's the accuracy or the tolerance they're asking for. So like if you're doing like coding, usually you can program the amount of tolerance into your solutions, right? Instead of saying go 1,000 iterations, you can say go until I have this level of accuracy, up until the 10,000th place or something. All right. This will be the same thing. Just could we just subtract them and then use that as your function. Let's do number 8, I guess. It looks like it already has a problem. Maybe this one be better. Let's do this one more time. Example 2. Calculate 2 iterations for f of x equal to cosine x. Using Newton method. Okay, so remember we said we need the original function. We need an initial guess. So either we guess ourselves or they give it to us. In this case, they gave it to us. We need the derivative. So if the derivative does not exist, we're not going to be able to do this. Okay. So the derivative of cosine is negative sine So x2 will equal x1 minus the function at x1 over the derivative at x1. So that will be 0.7 minus cosine at 0.7 over negative sine at 0.7. I wrote that all stupid. So using your calculator, at this point, there's no point in doing it by hand. At least that part. You're going to get 1.8872. So this is x2. So now start with x3. x3 will be x2 minus the function at x2 over the derivative at x2. So this will be 1.8872 minus the function at 1.8872 divided by the derivative at 1.8872, which will be approximately 1.5598. So they'll tell you how much to round. So in this case, they said four decimal places. Is there any questions on this? Is it pretty straightforward? Okay. Yeah, I mean, it's really just a formula, so I'm hoping it's not crazy or anything. It's not like freaking related rates or something. I think that's the hardest section here. Okay. That's pretty much. It's pretty much it. I mean, I think I'll save the review for next time. Do you guys have any questions from your homework that you're struggling with? Any issues that you're having at the moment? You can use the rest of the time for questions if you have any. Okay, well, if you want to head out, you can. If you want to stick around and do some homework, let me know. If not, I'll see you Thursday for exam 2 review.
Have a good day.
You too.